Hi, my name is Manish Gupta, and in this video, I'm going to talk about Mamba, which is linear time sequence modeling with selective state space models. Okay, so this is a pretty mathematical presentation. So, if you don't like maths, don't watch it. And also, this basically assumes a whole bunch of basics about transformers, RNNs, LSTMs, and things of that kind. Okay. So that let me get started. Finally, this is also a combination of about 3 to 4 papers, bits and pieces taken from various places, so as to actually understand how does this Mamba model work. Okay. Now, why is this important? So Mamba is important because uh, it is, I mean, because the results that they show at the end, which basically are like it can support 5x throughput compared to standard transformers. It can handle very long sequences, up to million size sequences, right? And it can also be trained very, very efficiently. And it basically shows better pre-training and fine-tuning accuracies compared to transformer-based models. Okay, so that's why this thing is this. That's why this model called Mamba is important. Okay. So let's sort of start from the very basic. Mamba is based on this basic systems called as these basic systems called as state space linear systems. Now these systems are not very popular in computer science, but are popular in other branches like control and so on, mechanical control and so on. Okay. So now what does a state space linear system mean? So it's a system of this kind, and let's think about from a perspective of an analog system, right? So this is not like a digital system; it's a natural, continuously varying system. So which takes some input U and tries to come up with a prediction for the output Y. Okay. So the input U could be something like some continuously varying quantity. So let's say temperature, right, in some ways, and output Y could be uh, something that depends on temperature in some ways. Okay, so essentially that's that. So maybe fluidity of some material or something like that, some property that depends on temperature. So it takes input U, which is analog, continuously varying, comes up with an output Y. And then it tries to model this dependence of y on u using these four matrices or four different parameters a, b, c, and d. A, B, C, and D. Okay, it's a non-deep learning system. Of course, remember it's a system. It's called state space linear system because it basically takes you. There are these matrices, or rather, there are these. Yeah, I mean matrices. In fact, A, B, C, D, which try to parameterize the system. Okay. So I mean, in fact, here the matrix B is basically an input matrix. So let's say if there is a input U, and the input U, I just mentioned temperature, but there could be P different quantities that you're measuring. So input U actually is a vector at any time point T. It's a function, right? So it's a continuous function. So at any time point of T, you can measure this input U, and let's say there are P different things that you're measuring. So that's that. And then at the output, of course, you want y, and y can actually contain more than p or less than p. So y could basically be of size q. So it may not be of the same size p. Okay. And in between, there are these state vectors. So basically, the idea is to say that the variation bit from u to y can be captured in terms of some state representations, and there are therefore these state vectors called x. Okay, and they have a dimensionality n. Okay. So that's that. So P inputs, Q outputs, and state variables. Okay. Um, so the idea is to basically take your input U and the current state X and try to come up with a new state, right? So current state X and try to come up with a new state called X dot, right? And then also come up with a final output YT. Okay. So using these A, B, C, D, these four parameters, right? Now, as you see, these four parameters, besides x and t, which are of course time dependent, these four parameters are also shown in a time dependent manner. Okay. So if you basically show them in a time dependent manner, it's basically called as continuous time variant state space linear systems. But if you show them in a non-time dependent manner, if they're constants like A, B, C, D, like they're shown there, it's called as continuous time invariant systems. So basically saying that these parameters A, B, C, D are time invariant in these kinds of systems. Okay. Of course, this one is much more generic, the continuous time variant one, but more complicated as well, because then you have to estimate these parameters A, B, C, D in a time variant manner. Right? So that's that. So essentially, so I was talking about the matrices. B is the input matrix. C is the output matrix. It decides how the output can be decided. A is the state space matrix. So A is the most important matrix here, which because it sort of explains how the system sort of moves from a state A to a state B in that sense, right? So from particular state, previous state to the next state. Okay. So the state is represented using the state vector of size n. Then of course this matrix, state space matrix, transition matrix should be n cross n, because it sort of captures how your state system transitions from one state to another. Okay. So that's that. Now input matrix is of size n cross p, because well, you have p inputs and you have n states, so you have to do a mapping. So that's n cross p. Output matrix is q cross n, because you have to map a state of size n to an output of size q. And then you also have this matrix D. There's an interesting matrix D at the top, which basically is also called as the feed through or feed forward matrix, because it directly feeds the input to the output without passing through the states. So it's sort of like short circuiting the entire state computation, and just says, hey, maybe there's a direct dependence between the input and the output, a linear dependence at that, right? So that's that. So they are called as linear systems overall, because it's all completely linear, except for this small little thing that the revised state x dot is basically a derivative over x, or derivative over x, right? So that's that. Now these are again sort of non-deep learning based systems. And they are continuous in nature. So you can continuously keep evaluating, inputting your u as a function of time, and then try to compute y at any point of time. Okay. However, for most text-based things, what we care about is discreteness, right? So essentially, we don't want to care about continuous time, but what we care for is recurrence in terms of discrete text inputs. Okay. So, and there is also a relationship between these kinds of systems and CNNs, but we'll talk about that later. So what I want to first talk about is that if you take such a linear state space model, or basically a state space linear system, you can try to map it to a RNN, which can either be a fixed RNN where A, B, C, D are determined using some closed form, or it could be basically a learnable one, and therefore it's basically then a recurrent not just a recurrent network, but a recurrent neural network in that senses. Okay. Now, as I also mentioned, that you can also look at these state space models as CNNs, but that's something that I can talk later. Okay. So the idea is that if you want to convert these continuous systems to recurrent models, which are discrete in nature, you need to use some sort of discretization function, some sort of discretization logic. Okay, and I'll not talk about the mathematical details about the discretization logic, but then this will basically bring in an extra parameter called delta t, right? Because delta t is going to capture your discretization interval in that senses. Okay. So basically, we are going to take the original parameters A, B, C, D, and then hey, we are going to say that we also bring in an extra hyperparameter called as delta t, because it tells you at what time points you're going to discretize, and therefore, come up with a discretized version with A bar, B bar, C bar, and D bar in that senses. Okay. And then for RNN, you can actually write the system as follows. So remember, x dot can now be called xt, and the x can be called xt minus 1. Because now we have a notion of time, which is a discrete unit, so which has been discretized in that senses, right? So, so xt is a bar xt minus 1 plus b bar ut. U are the inputs, remember, x are the states, right? So that's that. Now, so the inference can be performed efficiently by sort of computing the layer time-wise. So what you could do is to basically compute you can operate on one slice at a time. So ut, xt, yt, and then you can basically take your xt to really compute xt plus 1, and then you can consume ut plus 1. That's basically, this is just typical recurrent neural network inference, right? On the other hand, you can also look at it from a convolutional perspective. So you can basically, take your so your u at any point of time ut is basically a vector, right? So essentially, remember on the previous slide I talked about it as a vector of size p, but in general you could also consider it like another notation, vector of size h in that senses, right? So you could basically say that the training can actually be also in CNN. You can actually think about it as the original input u being passed, but the training is being done on one horizontal slice at a time. So which basically means that you can actually take U as the original input, do some sort of a convolution with some filter, it's a special kind of filter we'll talk about, come up with output. And remember, this is just a layer. So that output can further be convolved by another kernel. And then you basically come up with the next output and so on. Okay. So in this context, the notion of delta t can be considered as the width of the kernel. So these kernels are going to be special kernels. We'll talk about them later in brief. But the point is that you can think about the convolution operation as operating on all of those inputs in inputs u, right? All of those inputs u, and then coming up with the output y in one go, in one layer. And then, of course, the next convolution applies for the next layer and so on. Okay, so now let's come back to the recurrent model and try to understand a few more things. So as I mentioned, when you think about it from a recurrent perspective, you can call it as a linear state space layer. It's a recurrent layer, right? Which takes five parameters, A, B, C, D, and delta T to discretize stuff. Okay. And then you use some standard forms of discretization so as to basically get these discretized things, A bar, B bar, C bar, and D bar in that senses. Okay. So once you have that, now you can basically consider. So let's bring in some notations to understand the recurrence properly. So input U is of size L cross H, where each of those inputs, each of those things is basically of size H. So here it is a size H input, this is a size H input, and so on. So essentially saying that there are L such the length of the sequence is L and the dimension of each at each time point is H, right? Now, when you have these, if you really think about these recurrent models, RNNs, if you remember, this hidden layer basically is just a linear, I mean, it basically has H dimensions, right? However, in linear state-based models, this recurrent state xt minus 1 is basically going to be a matrix in that sense, is H cross n. So it's basically not a small sized layer in that senses, but it's basically H cross n. It's basically a full, a large matrix in that senses. Okay. So if you remember from the recurrent neural network days or other recurrent neural network model, basically this is how I would typically draw a recurrent neural network model where the input basically is just fed to the hidden layer, and then the one hidden layer talks to the next hidden layer, and so on. And then each of these layers was basically just a simple little thing with dimension h, right? But now remember, this is of dimension h, and each of these is of dimension h cross n. So that's the interesting part. Overall, there are totally L inputs, totally L inputs. Okay. So that's that. Now, why h cross n, right? So essentially, the idea is that in a typical traditional neural network, traditional RNN, you can only capture dependence of the current state on the previous state, right? So in some ways, there is a vanishing gradient problem in some ways, right? Essentially, and also you are trying to express the entire previous history in a single vector of size h, right? So that's what you do. However, here, I mean, in a linear state space layer, what is attempted to be done is to basically have these states be dependent on all previous inputs, okay? Not just on the current input and therefore, the previous hidden state, but actually be dependent on all previous inputs. Okay. Now that would be humongous and variable because at every time point, the size of the previous inputs differs, right? So the number it gets added by one. Okay. And therefore, what they do is to cleverly represent or compress this memory of all previous inputs using fixed size n parameters for it. Okay, so essentially, the idea is that if you really look at these u's, there is U1, U2, U3, U4. I mean, of course, U is actually a matrix, right? So it's basically L cross H matrix. So if you essentially just, and let's call those H things as H features or H dimensions in that sense. So U is basically H dimensional in nature and of course temporal in nature, right? So if you basically look at each of those dimensions in U, there are so many previous values of that dimension, right? Previous time point values. Now, you can sort of represent those as n different values, fixed, constant n different values, by sort of coming up with some sort of a coefficient over n polynomial functions. Okay. Now, again, this is mathematically pretty complicated, but let's not get into the mathematical complications. I mean, the idea is to be able to compress your memory of a variable sized memory of each dimension of U into a fixed size n dimensions, right? N numbers, n numbers. Okay? And these n numbers, technically, they represent the coefficients over n over a basis of n polynomial functions. Okay? Now, of course, what do you want to preserve from this memory? You want to make sure that you optimize for some objective W over this memory, right? So there needs to be some sort of a objective for compression. I mean, otherwise you can basically just say, hey, let me just take the latest n and let's call it done. That's a good compression. But sometimes maybe the oldest one is most important. So you want to have some sort of a objective function which decides how important each value was in the past, and that thing is captured by W. So therefore, this notion of representing the entire past in terms of n different numbers is conditional on an objective function W. And the way it is computed is actually called as Hippo. So it's basically called as high order polynomial projection operator. So this operator essentially knows how to take your previous time point values, entire past, and project them onto an n-sized vector, right? So take a vector of variable size and project them onto n-sized vector by caring about n different basis polynomial functions. Okay, so that's that. Now, again, how does Hippo work? We are not going to go into details of that, but there's an interesting paper linked from there, which you can read if you are really, really mathematically inclined. Okay. So now to think about, so coming back to this system, there is A, B, C, D. So, and the idea is that A is a n cross n matrix. So essentially, remember, n is the state size. So A is n cross n because it's the state transition matrix in some ways, right? In some ways, you can also consider C as an emission matrix because it's like emitting the output, right? And it's basically 1 cross n because the idea is that if you're given a single U, think about U as a single number. So if the input was a single number, right? If there was only one dimension, then you would want an output of size 1 as well, right? So basically, that's what C is doing. And what does D do? Well, if basically your output is also a single number, then D must be also a single number, right? So the D guy must be able to just map the U to an input, to an output. Okay. So basically that's that. So essentially it's taking the input U and then just coming up multiplying with a single number to actually get a Y. Okay. So for the sake of this discussion, the current discussion, I'm just basically considering one feature in the input. So therefore, just one number in the input, one number in the output. Okay. Now C, basically there are n state variables, and you want to figure out how much importance to give to each of them. So that's C, output matrix, output vector C in that sense. Okay. Now the idea is that if so that's how a single SSM works, a single state space model works. Okay. Now when I mean a single state space model, I mean something that depends on only that processes only one dimension. Okay? So one dimension input. So if you don't think from a deep learning perspective, your A can actually be set to this kind of a matrix. So A is a matrix, n cross n matrix, and the way you would initialize or set the A is using this kind of a function. Okay. So where does this come from? Well, this comes from the Hippo theory. It basically says that certain kinds of matrices allow for compressing all the past into n different numbers such that the optimizer function W. Well, so this particular A, the state, the form that you see is a particular such Hippo compatible matrix A. Okay, so that's that. Now, if you basically have inputs with multiple dimensions or multiple features, so I just talked about one feature. If you have multiple features, let's call those as H because that's what we call them. So H different features. Then what you need to do is to basically just create H copies of B, C, and D. So you don't need to touch A, remember, you don't need to touch A, but you need to make H copies of B, C, D, of course, delta T. So there's delta T as well, which basically tells you, discretization factor in that sense, the discretization interval, right? So so there is BCD and delta T, and then there are these H copies. So because you have to run a state space model per feature. Okay, so essentially, in fact, if you have understood so far, what I've tried to explain is that each state space model works per feature, and the features don't talk to each other at all. Now that's a bad thing, but that's what it is, right? So the features don't talk to each other at all. Okay. Now, but that's bad, right? Because of course, in text embeddings, for example, we know that features, of course, are dependent on each other. The individual dimensions in the embeddings are dependent on each other. So this is a bad thing. Okay. However, there is a way of avoiding this bad thing. So I'll talk about that way now. Okay. So you can, however, currently, I mean, if you basically are okay with this understanding that yes, you have these features which don't talk to each other, you basically can, the way you would train the deep learning way now is that you can fix A and you can fix delta T, right? Or you can train them. So you can basically have them both fixed or train them. At any point of time, BCD are always trained. Okay, so you will train BCD. However, you may or may not want to train A. For the simple reason that A is n cross n, so it's very large, so it may take a lot of time to train it. Okay, so therefore, what people typically do is to initialize A and delta T. So A is initialized using this hippo kind of a stuff, right? So the hippo thing, and delta T is actually initialized log uniformly on a range min to max. Okay. So you fix a range min to max, and then you basically ensure that if you take these delta log of these delta T's of these values, then they are uniformly spread out between min and max. Okay, so that's that. So you initialize A and delta T, or you fix them, right? So either you fix them or you train them. So if you train them, then you initialize A and delta T with these values. BCD can be randomly initialized, and you train them like a standard RNN model, okay, using backpropagation and so on. Okay. So now so the interesting part is that there was no mixing going on across the features, as I discussed in the previous slide. Now, if you have to enable mixing, what you can do is the following. You can still, let's say if you had like one dimensional input U, it need not necessarily always have one dimensional Y. And the way you can change that is by changing the emission parameter C. Okay, so what you could say is that, well, C is M cross N. And if C is M cross N, and of course you have to also change D. So D is M cross 1. In that sense, what would happen is that one U can actually give you M different Ys, okay? So that's that. However, if you have M different Ys, then there's a problem because you, of course, only wanted a single Y, but now you have M Ys. So what do? You basically learn a very simple dense layer, which basically takes your M different things and gives you a one single thing out of it. So M different things and gives you one single thing out of it. Okay. Or now, if you really start thinking about it, if you have H features, you have HM as the overall output, and what you want is the size H output. And what you can do is to take this HM, output from the SSM and then combine it with a dense layer, which basically gives you H-sized output. You know, in general, incurring an extra h square m parameters, but then also doing mixing across features. You see the mixing is going on across features here, right? So that's that. So this is basically how a single SSM layer works. A single SSM layer, a state space model layer, basically contains this computation in these senses. So essentially, you take the input U and you get the output output Y, and then you wrap just like you do in a typical transformer layer. You have the layer normalization and residuals. You can actually do that. Okay. And that basically gives you a single SSM layer of this kind. Takes U, gives you Y, but also has like normalization after Y, and then there is residual also and so on. Okay, all of those things. Okay. and it has these parameters. If you had this mixing parameter m, so that basically gives you m, and then h times h plus n. So remember, h square actually came up because of this mixing thing, but h into n came up because your b and c are h into n, right? In that sense. Okay. Okay, so basically this one does not have n square because you treat a as fixed. You don't really learn a, right? So you just fix a in that senses and you don't learn a. Okay. Because learning a is too cumbersome. It's basically very, very computationally expensive. So we later will see how this can be avoided, but you don't learn it. Okay. Uh, so in this paper, they basically talked about two variants of LSSL models, small and large, with 200K and 2 million parameters, respectively. 6-layer, 4-layer models. Of course, what you do is to basically then stack layers of this kind, multiple layers, 4 layers or 6 layers, and you essentially obtain, larger multi-layer linear state space models. Okay. Um, so you could also have nonlinearity, by the way, in this layer. So after this layer, basically you can actually have some sort of a activation function. So nonlinear activation function, which brings in nonlinearity in the entire system. Otherwise, the entire system would just be linear. So which is too bad. So you can bring in nonlinearity in this mixing matrix also. Okay. Now, yet another way of looking at these systems is basically in a convolutional manner, and which is what is explained here. So remember, this is the recurrent way of looking at it. And then if you really try to take this entire thing, if you basically take this entire thing xt and you try to plug it in here, and you keep plugging in several times, infinitely, right? Several times or rather, multiple time steps, not infinitely, L different time steps, because L is the size of the sequence, right? Then what you get is this. So you can basically say yk is, you see dut is basically just there. And you see, if I put in b bar ut, I get that. And then, I have like a bar, but then there is also xt minus 1, which can be further expanded and so on. So I basically get like, of course, this part anyway, and then the a bar and the c, because c comes from there and so on, right? So you get that. Now, you can then basically think about yk as, and as you observed here, there are u0, u1, uk minus 1 up to uk. So you observe that part, right? So you can think about, therefore, these parameters, you can group them all together into a single kernel. This kernel is called as Krylov function. So you basically combine all of them to a single kernel, and you convolve with the input u. So you convolve with the input u. So you could think about this element-wise multiplication as a convolution in that senses. And that helps you think about linear state space layer as a convolution operation. Okay. Now that's that. Now let's basically see what people did further to make sure that this can be trained efficiently using deep learning kind of operations without fixing A, yeah, but just initializing A. Yeah. So the bottleneck in using these state space models is that you need to repeatedly multiply by A bar, right? So this A bar matrix, which is a discretized version of A in that sense, is basically is large, and this repeated multiplication basically causes n square L time, right? So essentially you have to multiply, L different times. L different times just to get these kinds of matrices, and well, they are n squared, so therefore n square L time and NL space, right? So what these guys do is to reparameterize A by decomposing it into these two parts. Okay. Lambda and PQ transpose. So such that each of these three parts, lambda and P and Q are n in size. Okay. So what does this mean? This basically means that rather than having n square parameters in A, you're basically having 3n parameters in this reparameterization. And of course, you have parameters in B and C. So that's what that's what it means. Okay. So specifically in this paper, I basically said that you use some discretization function, the discretization function which has become popular these days. Okay. So you take delta and A, and you get A bar. You have some sort of weirdish looking function. You basically get like B bar. Okay, that is how this discretization is typically done. Okay, so that's that. Now, so basically, as I was saying, you avoid this n square A by actually decomposing it into 3 n-sized vectors, lambda, P, and Q. And that totally gives you 5n parameters, because 3 for A and then 1 for n for B and n for C. So that's basically 5 n parameters. Now, later people also realized that rather than using a different Q, you can actually just use the same P. So that basically makes it even better accuracy-wise and or stability-wise. And that basically gives you lesser number of parameters also. Okay. So even though you're going to now use deep learning to update all the parameters, rather than A, now you have like lambda, P, and Q, and B, and C overall, right? So you want to update all the parameters, and of course D as well. So you want to update all of those parameters, but you still initialize with hippo. So you start with the hippo initialization for A, and you do reparameterization or a sort of a decomposition into this lambda and P and Q, and then you use them for initialization, right? And then you essentially learn them over time using backpropagation. Okay. Turns out it's a great initialization, right? So, and then of course, just like you did in the previous LSL model, the standard state space models, you also do the same thing with these S4 models. They're called S4 models, structured state space sequences, because you're structuring out your A into a particular kind of a form, right? So you have layer normalization, you have residuals, and then residual connections, right, in that senses. And then the total number of parameters does not change. It's basically the same. But what changes is that you're also trying to train A now rather than keeping it fixed. Okay. Now, these kinds of models are also called as linear time invariant models, as I mentioned on the first slide, right? So if you look at A, B, C, D and delta, right? So all of these, I mean, you can actually ditch D if you're actually doing residuals also. So therefore, starting from this paper, you'd observe that people only talk about A, B, C. They actually forget D because, well, D is more like residual. D is like a direct connection from input to output, and you can actually have that separately as well. But people don't bother about D anymore. Okay. So remember, D was a direct connection from input to output. And if you basically have an expressive enough ABC, you really don't need D. Okay. So that's that. So as I was saying, these models basically have linear time invariant ABC. So ABC don't change with time. The same ABC are usable across different time points at inference time. Okay. So this is interesting, but has some drawbacks as well, as I'll discuss later. Okay. So, but based on this kind of SSM understanding, the state space model understanding, there have been several papers which have come up, several architectures, which are some of them notable ones are these ones: linear attention, H3, Heiner, RetNet, RWKV, and of course, Mamba, which I'm going to talk about, sometime later in this video. Okay. So far I've just talked about what are state space models, and I have basically told that state space models can actually be trained efficiently and inferred efficiently by actually using this hippo initialization, also thinking about them as equivalent in terms of recurrence or convolution. Okay. The interesting part is that unlike attention, these state space models can actually handle very long context lengths. They compress context into a small state, right? Attention does not compress context at all, right? It basically keeps those key value caches forever, which basically makes it quadratic in complexity. But these state space models basically can handle very long context lengths. Okay. Here's a nice illustration to understand this more clearly. There is nothing new in this slide. It's basically the same as what we have discussed so far in S4 model. It's just that it is a nice illustration using a picture, right? So there is an input here, and as we discussed, there is basically an input layer, so which basically has L inputs. Think about them as L different words, input words. In translation, for example, English to French translation. So you basically take English words, L different words, each expressed in a case in a H-sized embedding, right? So this is H. This is H, right? H-sized embedding. So that's the input, right? So what you do is to basically take this input U and take the previous state X. So remember, X basically is H times N. So it's not like it's basically a matrix by itself, H cross N matrix, right? And then what you do is to do this recurrent computation. So A bar xk minus 1 plus B bar uk, right? So, and the way this is done is that you apply individual SSMs separately per dimension. So what is the dimension? Dimension is basically just one unit from each of those L time points. Okay. So therefore, you see that there is and if you really think about it, this is basically A bar for the first feature. This is A bar for the second feature. This is A bar for the third feature, and so on. And that is why you basically see them as arranged in a diagonal form in that sense. Okay. So that's that. Now, essentially what you have is h n square matrices that you see there, right? But of course, as we discussed in the previous slide, you don't store them as n square matrices. You basically store them as 3n sized vectors, right? And then you also have these, h n sized h n sized b's, okay, h n sized b's, okay. And then on the other hand, so basically you do all of that, and that gives you the revised state space representation, right? Now, on top of this revised state space representation, you can actually do CXK, so as to essentially get the emissions YK. So again, that makes use of this matrix C, right? Again, basically for each of the H dimensions, you have n-sized vectors, right? So you apply nonlinearity after that, and you can actually do a mixing layer. So as we discussed on the previous slide, you can actually mix by, if your C basically gave you, if your C basically was not just a vector, but more like m cross n thing, But nothing stops you from mixing even otherwise. So even otherwise, even if you basically just get, let's say, a h-sized y, even if you get like a h-sized y, you can still do a h cross h dense layer and then have those dimensions mixed with each other. As simple as that, right? So that's basically a mixing layer as well. So as you see, if you really think about learnable parameters, everything is learnable here. A, B, C, your mixing layer, all of them are learnable. Okay? Unlike the LSSL model, which was proposed way back in the beginning, where A was not learnable, right? You couldn't afford, and there was no mixing layer in that sense. Right? So that's good. Now, of course, this is a single S4 layer. So after you get the output from the single S4 layer, the notations are slightly different. So please don't get mixed up with the notations. So after you get the, the output from the single S4 layer, which is basically this becomes input for the next S4 layer. And as we discussed, S4 layer, basically S4 models can actually have several of such S4 layers combined. Okay, state space layers. Okay. Not the problem with S4 models, right? So as we discussed earlier, S4 models are linear time invariant, which basically means those parameters basically are not functions of time, okay? Which causes trouble. So which basically means that these parameters cannot perform content-based reasoning. So essentially, they perform the same reasoning irrespective of whatever is the content right now, okay? And in recurrent models, typically that is done for a particular reason, right? So essentially, you want the unit to be recurrent in nature. So you basically, therefore, don't make them time dependent in that sense. So that you can actually use the same matrix forever, right? However, this basically causes trouble. So for example, these kinds of models, S4 models, can do copying nicely. So if you had some sort of a string in the input, let's say this part, and you wanted to avoid this entire stuff, but just copy in the output as is, yes, you can actually copy them nicely because it knows exactly that, hey, it has to take this input and put that at the output, take this input and put that at the output, and so on. So I'm so sorry. So the input is actually mentioned here. So you basically, if you want to just copy, that's possible because it basically knows, it basically learns what is the distance between copying, and it can actually respect that distance and copy sequentially nicely. Okay. But let's say if you want to do selective copying, what does selective copying mean? Selective copying basically means that the input is like that, and the boxes are distributed with gaps between them, and you want to sort of copy them. Now the model does not know that it has to ignore and not copy this stuff, especially if the gaps are random in nature, right? So whatever kind of training you do, the model will not be able to know that it should not copy that stuff, right? So therefore, what is important to do is so this is basically called selective copying. This task is called selective copying. Basically, you selectively copy certain blocks. Okay, selectively copy certain blocks depending on the current input. So for example, if you are doing speech to text and there are ahs and ums and so on, in that speech to text, you want to ignore all of those random speech interjections, right? So now selective copying is exactly that and cannot be done using standard S4 models because they don't have those parameters which are time dependent, right? Which are dependent on the current inputs. Okay. So yet another kind of examples, yet another kind of task is this task called induction head task. The idea is that in the input, if you basically observed some part of the input, and let's say at some point, you observe the black box again, your associative memory should tell you that after black, blue comes in. But in general, it's very difficult to sort of implement this associative memory with S4 models, because S4 models, again, do not really care about what is the kind of current input, right? They only care about using the same parameters on whatever input comes as whatever thing comes as input. Okay. So what you want is some notion of attention. Okay. So that's the most important part. You want some notion of attention. Uh, so attention, of course, in transformer models is effective, as we all know, but it is inefficient. Inefficient because the transformer models don't do any compression. You want compressed memory, but you also want attention. That's the interesting part you want. Okay. So recurrence is efficient because it compresses the entire history into a small state, right? Now, of course, in the standard recurrent neural networks, it compresses it down to a H-sized single layer, which is really bad. But SSMs, the state space models, could compress them into H into N using that hippo kind of approximation, which very effectively compresses the memory, right? But can you compress the memory better in an attentive manner, right? That's the idea. And that is the main idea behind Mamba, actually. So behind what is called as S6 models, S6 layers. And these S6 layers basically lead to Mamba. Okay. So what is the solution? The solution is to have these SSM parameters. Some of the SSM parameters may not be all of them. Some of them, like delta, B, and C, be functions of input rather than be fixed over time. Okay. So now, again, this is still pretty mathematical, but not too much. So let's try to intuitively understand what's going on here. And here, let's start from here, right? So you basically have a continuous state-based system with parameters A, B, C, and delta. And what you want to do is to discretize them first. So the first step is just discretization. This is called as some zero order heads or some such ZOH optimize ZOH discretization. Now, again, I'm not going to go into details about how that works, but or other why it is this way. But the idea is that you do some sort of interpolation and things of that kind, so as to basically get this discretization, right? So you basically get A bar and B bar. Okay. So this is basically the standard analog form, and this is the form of recurrence after you discretize. And this is the form that you would care for if you cared for convolution, which we don't care for in this particular slide, right? So we don't care. Okay. So standard S4 layer does the following. It basically takes input X, comes up with output Y. Input X has L different time points, right? So L different time points, L different words in input, each with D dimensions. So yeah, I mean, notation is a little bit of a problem, but bear with me. D is the dimensions. We used H earlier, so it's D here. So D is the number of dimensions, okay? And B is the batch size. So let's say you're passing on a batch of 10 input English sentences. And each of maximum D size. Each of maximum L size. Each sentence has maximum L words, and each word is represented using D-sized embeddings. Okay. Now, so if you basically think about these parameters for Mamba, you would basically have D different SSMs, D different SSMs, because dimensionality is D. And for each SSM, you will basically have a matrix A, B, C. So A is a overall n-cross-n matrix conceptually, but well, I mean, when you try to reparameterize it, it becomes a n-sized vector, right? Well, I mean, earlier when I mentioned, it basically becomes 3n-sized vector, one for lambda, one for p, and one for q. But later, people also came up with other variants where they could express A as a single diagonal matrix, which basically means that you just have one n-sized vector. Okay. So for D different SSMs, you have dn-sized parameter. Okay. Similarly, B, C, they are also dn-sized parameters. Delta is basically a d-sized parameter, one for each SSM. Okay. You take those, you discretize them using these discretization formulae right at the top. And that basically gives you your discretized A and B, and then you run the SSM, basically some sort of recurrence or convolution. So you could do this recurrence or you could do this convolution. So as to essentially get Y, and you return Y. So that's basically a SSM S4 layer. It's a single S4 layer. Okay. Of course, it's not a complete S4 layer, but an SSM in an S4 layer, because you would also do layer normalization and residuals and so on. Okay. So that's that. Now, how does the S6 layer differ? So remember, in S6, basically S6 stands for SSM plus selection with a single scan. So there's the 6 S's in it. Okay. So the input and output don't change, they're just the same. But remember, your parameters, your parameter A also does not change, still is the same. But B, C, delta are actually going to become time dependent, or rather input dependent. Okay, so essentially you have X as the input, remember. So you have B as the batch size, L as the sequence length, and D as the dimensions. For each dimension, what you do is to basically use the parameters D cross N parameters so as to map D to an n-sized vector. Okay, you map D to an n-sized vector. So your B, if you look at B as such, what has happened is that although the learnable parameters are just D into N, but when you multiply, when you actually take your input, which is of size BLD, you don't basically involve B and L dimensions into the transformation, but you transform D to N size. Okay, and therefore it gives you an output of BL N size. So what you've done is basically you use DN parameters so as to in this function, so as to essentially convert your X to B. Okay. Of course, this is a very large sized B now, but as you notice, for every input in the batch, for every sample in the batch, and for every position L, what you have done is to basically come up with a parameter B, which is dependent on the input. Okay. The same thing you do for C as well. So what is this SBX? SBX is basically a linear projection, such that you fix B and L, but project D to N. Okay. So that's that. So it's basically a parameterized projection to dimension N in that sense. Okay. Now, the same thing you also do for delta. So delta in general is just a number. And for different SSMs, you will basically have D such numbers. But what you do is to take this number, you have a linear dense matrix, broadcast it to D. I mean, just like you broadcasted it to N here, you basically, or rather, you convert it to linear N here, you actually do a linear layer. Get a single output, and then you broadcast it to D. So you basically just use the same D things. Okay. And have a parameter per dimension, and that is what basically gives you the overall delta. So delta which is dependent on the input. Okay. So that's that. Now, and the remaining part is the same. So essentially, once you get those input dependent BC, and A and delta, you actually run the typical discretization and then the SSM. Of course, they also do a very, very interesting stuff by doing an efficient GPU implementation. So GPU has SRAM, and also it has like faster register memory. So they basically ensure that they do the heavyweight computations, like even like discretization and the SSM computations all in this faster memory, and only dump the larger outputs that get generated to the SRAM, okay, to the slower memory. So that's that. So what is Mamba's architecture? Well, Mamba basically comprises of these S6 models. Okay, so this is the S6 layer. So Mamba basically uses an S6 layer in some ways because it has these parameters B, C, and delta, which are X dependent, which are dependent on the current input. They basically incorporate attention in that senses. Okay, so or rather they incorporate selectivity rather than attention. I should call them selectivity. Okay. The Mamba layer basically comprises of, this is the architecture for the Mamba layer. Okay. So the S6 model that we talked about is there. So this is S6 basically. Okay. Of course, nobody stops you from using S4 here. You can actually also use a S4 layer or a simple LSS layer as well here. However, the idea is to basically use S6 for best results. Okay. So this architecture actually it starts with the input U here. It basically which is let's say d-dimensional in nature. So it uses a dense layer to convert it to E dimensions. So at that point, so it has this expansion layer to actually expand D to E, and typically they keep E equal to 2. So in the sense, and the expansion factor. So this is basically E times D in that sense. So expansion factor is E. So they typically keep E to D. E to 2, which basically means you expand your input size to 2D, of course, involving learnable parameters in that senses. And then you use essentially like a convolution layer and an SSM. So this convolution actually The reason why it comes here is motivated by another paper, H3 paper, as it says, right? So it's basically motivated by this H3 paper. Now, if you want to know more about why that convolution thing is there, you will need to read the H3 paper. But very broadly, right, that convolution is also another SSM in that sense. Remember, I told you SSMs can be expressed in terms of convolution. The convolution is also SSM. The H3 paper, very broadly, what it does is to basically think about these computations as starting from you computing QKV, just like a typical QKV transformer attention does. Computing this similarity between Q and K using some sort of a SSM layer, using this convolution operation in that senses, and then having further operation on top of that with respect to V using another SSM, right? So essentially, the H3 sort of architecture has this notion of convolution followed by an SSM, which is what is borrowed here. Now there is this other path also, and this path basically comes from yet another kind of work called as gated MLPs, gated multi-layered project perceptrons, right? So where this is the mainstream main channel or the main sort of path, right? And then this is the gating path on the right side. So it basically tells you that whatever outputs are coming from here, which of them should be allowed to pass to the final output. Okay. So in some ways, for every output that you generate, there is also a control, gating control, which decides which ones to pass, which ones to not pass, right? So basically what Mamba does is to combine this H3 and the gated MLPs into a single architecture called as a Mamba architecture. And this is the Mamba layer. So the single Mamba layer. Now, of course, you can actually build multiple Mamba layers and then therefore build larger Mamba pre-trained models. This is basically, these are pre-trained models that are publicly available. 130 million parameter models, 24 layers, up all the way to 2.8 billion parameter model, 64 layer models. Okay, with different model dimension sizes. Now that's that. So you can think about, so these deltas basically which were there, they are used to control the balance between how much to focus or ignore the current input. Remember, essentially you're doing selectivity by trying to have these B, C, and delta dependent on inputs. So the delta essentially can be interpreted as a good control in terms of how much to focus on the current input versus forget the current input. Okay, so that's that. And of course, your B and C essentially are also working at the input and the output side. So how much to actually care about the current input in terms of selectivity, how much to emit whatever is learned from the current input onto the output and so on. Okay, so how does Mamba perform? So, of course, the motivation for Mamba's selectivity was from two tasks: the copying task, selective copying task, and induction heads task. If you compare, so in the selective copying task, just to recall, you randomize the spacing between tokens which have to be copied, right? And in the induction heads task, well, it basically, there's a reason why it got this name called induction heads. The reason is that, or rather, first let me tell the task. So the task is that if there was some piece of text in the context and it contained a bigram Harry Potter, so if you basically want to complete the next word after Harry, let's say later down in the text, again, the word Harry appears, it must complete with Potter. Okay. So this is called induction heads task, and it's called induction heads task because a typical transformer model, thanks to multiple layers can actually, and attention heads can actually learn this task very well. So in the current layer, in a transformer current layer, one head basically just knows how to copy Harry, right? And in the next layer, the next head basically one head basically just does copying, and the second head basically just does focusing on the, so one head just focuses on the current position, the other head in the next layer actually focus on the previous position. The two heads across the two layers in general work as induction heads. They basically allow you to copy bigrams in that sense, right? So that is why it's called induction heads task, very easily doable by transformer kind of models, which basically have this attention mechanism, a perfect attention mechanism to pay full attention in one head on the current input and full attention on the previous position in the other head, right? So of course, the standard S4 model cannot do this because it doesn't have the selectivity notion, but a Mamba model can actually do this, right? So that is that. So the outputs are as follows, basically, or rather the results are as follows. So if you basically looked at the standard S4 architecture, if you basically just consider S4 architecture without any MLP gating and so on, what you observe is that with the S4 layer or S6 layer, you can actually obtain some kind of accuracies for selective copying. Of course, S4 is really, really pathetic. Even with the Mamba architecture, S4 is pathetic. But if you basically have gating, if you don't have gating, still you basically get like 97% accuracy on selective copying tasks with the S6 because it has selectivity. Right? However, with the gating, S6 accuracy improves even further. So with the full Mamba, it basically gives you really good results. Okay. So Mamba, I mean, now if you think about induction heads task, you can actually train it on sequences which are just 100 sized, but test it on very long sequences. So how well can it associate its memory over very long range sequences? Okay. So what can be the comparisons across several models, including Mamba, which is basically the brown line right at the top, right? Everything else basically drops down as your test sequence length increases. Okay. So the result is obvious. The accuracy sort of remains 100% or close to 100% for Mamba, but not for others. Okay. So Mamba generalizes perfectly to these million length sequences, as you see. So it's a million length sequence or 4000x longer than it saw during training, right? While no other method goes beyond 2x. So no other method basically learns how to handle sequences more than 2 times of training. Okay. Now people try to, of course, train Mamba on the pile dataset and look at perplexity. And perplexity wise, if you draw these perplexity graphs with the different sequence length, 2000 and 8000 in that senses, you observe that Mamba gives you the lowest perplexity. Lowest is the best perplexity. So that's good. Okay. So that's that. And basically, they also try to train it on, fine tune it on various tasks, NLP tasks. I'm not showing those details here, but I'm just showing the average accuracy. So these are various different kinds of models of different sizes. You see the Mamba ones which are highlighted of different sizes again on the pile data. This is all pre-trained on the pile data and then fine-tuned on some other tasks, 7 or 8 tasks, right? And what you observe is that Mamba models actually give you better results than GPT-2, than GPT-based models, GPT-Neo or OPT and so on. So, GPT-J as well. So, so Mamba 2.8 billion gives you like 63.3 on average, which is higher than any of these. But even higher than the popularly known Pythia 7 billion parameter models. Okay. So in short, Mamba 3 billion parameter model, or the 2.8 billion more accurately, outperforms transformers of the same size, Pythia model, right, OPT model, GPT-Neo model of the same size, and matches transformers twice its size, both in pre-training and downstream tasks. Okay. So here the comparisons, as you see, are also with transformer and more optimized versions of transformer and so on. Okay. So because of their optimizations while training, their efficient scan method, which basically appropriately allocates those tensors to appropriate parts of GPU, right? It's basically 40x faster than the standard implementation, which involves flash attention, of course, right? The inference is basically about 5x higher throughput than transformers, because unlike transformers, which need to manage those KV caches, Mamba does not manage KV caches, although it does manage large states, right? States are pretty large in size, but it doesn't have that KV cache dependency. The states are fixed in length, right? And therefore, it can actually use much larger batch sizes and lead to 5x more throughput. Okay. So in this video, in summary, I talked about state space linear systems, which are non-deep learning, non-machine learning, non-computer science things, basically popular in the control theory world. Right? So then I talked about how they have been adapted into doing NLP in that senses in terms of state space models with the linear state space layers. Okay. Then I talked about S4, which basically made learning of these systems efficient, right? By not just putting up a form on the way the matrix A is defined, the transition matrix A is defined, but also sort of trying to decompose it into linear factors, right? S6 model enabled selectivity, which basically is pretty good from an accuracy perspective. And overall, we observed that Mamba gives you state-of-the-art performance results across several modalities like language modeling. I didn't talk about audio and genomics, but there are experiments in the paper about that as well. Okay. Mamba it provides 5x higher throughput at inference time compared to flash attention too. Okay. So that's it for this video. Hope you liked it. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.